I think our next speaker is Albert, right? Albert from Nethermind, and he will be talking about folding for hash-based SNARKs, right? Am I getting it right? Yeah. Okay, thank you.
So, how do I flash the slide?
Yes, this one. This one.
This?
It's the green one.
Okay, thanks. It's a pleasure to be here and present the work we have been doing at Nethermind Research. So, yeah. So what will I talk about? What will I talk about? This is the outline. So, this work revolves around folding for hash-based SNARKs. Folding is a hot topic that has been intensely studied recently. So, the outline of the talk is the following. I'll give a crash course on folding, then I will discuss what are hash-based SNARKs, what I mean by that, and then I'll explain our framework for folding when you want to use a hash-based SNARK. Then this framework is kind of abstract, it's not instantiated, and then I'll explain how we instantiate it via lattices. And then I'll explain a trick we had to perform on the Nova folding scheme so that we could actually instantiate it with lattices. Okay, so what is folding? So a folding scheme, or also called reduction of knowledge, is an interactive protocol between a prover and a verifier where the prover has two instance witness pairs, and the prover and the verifier interact to create a new instance witness pair so that if the new instance witness pair is valid, then the two original ones are valid, except with negligible probability. So, to be more precise and start adding some notation, so in a folding scheme there's two relations, R and accumulated R. The accumulated R is basically the relation R, but with a bit of relaxation. So, in particular, the original relation that we care about is contained in the accumulated one. And the scheme transforms an instance witness pair from R and an instance witness pair from the accumulated relation into a new instance witness pair of the accumulated relation. And we write this scheme succinctly as R times accumulated relation goes to accumulated relation. So why do we care about this? So yeah, this blue thing is just so that we keep in mind what is folding. So the general idea when you design folding is to keep the cost of the prover and the verifier in the folding scheme at a minimum. And when you do that, you reduce the task. So folding reduces the task of proving two instances to proving one instance, plus proving that the folding was done correctly. So if you keep the cost of the prover and the verifier to a minimum, you are actually getting a faster prover time and a smaller proof, right? Because instead of proving two instances, you prove one instance, and that the folding was done correctly, which is cheap, because P and B are cheap, and you get a smaller proof. If you prove the two instances, you get two proofs. If you prove one instance and that the folding was done correctly, you have one proof and a small proof, and the proof of folding, which is usually very small. So if you can do that, you can do incremental verifier computation or even proof carrying data. You can also use folding to prove large instance witness pairs. So say that you have an instance witness pair that is too large to prove at once. Then what you can do is you can do the continuation strategy, so you break the instance witness pair into smaller pairs, and then you fold all these pairs together into a single instance witness pair. And then you prove this folded instance witness pair, and you also prove that the folding was done correctly. Okay, so folding became very popular since 2021 when the Nova scheme was introduced. So I'll outline how Nova works. I will not describe how it works exactly because if you haven't seen it, I think it's impossible to describe it in 20 minutes, and if you've seen it, you will just get bored. So I'll just give you the main ideas you need to keep in mind. So yeah, so for technical reasons, in folding you fold committed relations. So if you have a relation R that you care about, the committed version is just the original relation, but you add a commitment to the witness. And then your inputs to the committed relation are the original input, the commitment to the witness, and then the witness is just the witness. Okay, and if you want to prove that an instance is in the committed version, you just prove that the instance is in the original relation and that the witness commits to a public value. Okay. So in NOVA, the relation we care about is the R1CS relation, and the accumulated relation is the relaxed R1CS. In both of these, there's three matrices, A, B, C, and for the R1CS relation works as follows. So an input instance pair is in R1CS if and only if you have this equality between matrices. So A times Z, B times Z, Z times Z is matrix vector multiplication, and the circle is the Hadamard product, so component-wise multiplication. And Z is the concatenation of the input and the witness. And the relaxed R1CS looks similar to the R1CS, the original R1CS, but there's this error term, and there's an extra U in front of the Z. Okay, so how does the NOVA scheme work at a high level? So you take two instance witness pairs from the R1CS relation, committed one, because we have to work with committed relations when we do folding. And the first thing that the prover does is it computes a so-called cross-term vector. It doesn't matter what it is, so I won't say what it is, it's just a vector. It commits to it and it sends it to V. Then the verifier. Then the verifier replies with a random challenge. And now the new instance witness pair, the result of the folding, is this tuple in here. So the input X3 is the random linear combination of the two inputs of the original instance witness pairs. The witness is again a random linear combination of the original witnesses. And then there's some decoration that comes from the relaxation of the relation. The main idea here is that you take a random linear combination of the instance and the witness. And here there's a crucial thing. So the verifier needs to obtain the commitment to the witness, right? Because it's a committed relation. So how does the verifier obtain the commitment to the witness? I didn't say that in this scheme, in this outline. Well, it's quite simple. We require the commitment scheme to be homomorphic, which means that the commitment to the sum of two vectors is the sum of the two commitments. So if you have a commitment scheme with this property, then the verifier can compute the commitments to W3 and the error term just by using these linear expressions, right? If it has the commitment to W1 and the commitment to W2, you just follow this expression and you get the commitment to W3 with scalar multiplication and addition. Okay, so that's the NOVA scheme in a nutshell. If you're not familiar with NOVA, what you should remember is that NOVA requires a homomorphic commitment scheme, and that during the folding scheme, the prover commits to a so-called cross term. And it's also important to remember that this cross term is quadratic in the witness. So this is the expression for the cross term. There's these quadratic terms. There's some extra terms in here which are linear, but yeah, so it doesn't really matter what it is, it's just a quadratic expression of the witness. Okay, so let's say that we have done a lot of folding, and now the prover wants to fold an instance witness pair that has resulted of folding. So the prover now has to prove the following claim. It has to prove that it knows a witness that commits to certain public value, bar W, and that such that it is a valid witness for the input XF. Okay, so when it comes to this second claim, that's usually relatively easy to do if you know how to prove instance witness for R. If you have a SNARK for R, it's usually easy to adapt the SNARK so that you can prove instance witnesses in the accumulated relation. And the claim about the commitment is really easy to deal with because most SNARKs, most commonly used SNARKs, are already SNARKs for the committed version of the relation. So in most SNARKs, the first thing that the prover does is to send a commitment to the witness. And then it creates a proof for the instance witness pair with that commitment as published, referencing that commitment. So this step about the commitment is usually free. Yeah, so that's how you prove a folded instance witness pair. And this is very nice. However, we saw that the commitment scheme has to be homomorphic. And this means that the SNARK, so commitment scheme needs to be homomorphic. And here we are using that the first thing that the prover does is commit to W. And this commitment is this thing in here. So this bounds the SNARK that you are using to use a homomorphic commitment scheme. And then it is not clear how you can use this framework when you want to fold using SNARKs that don't use a homomorphic commitment scheme. For example, hash-based SNARKs. So what is a hash-based SNARK? It's a loose term I use to refer to SNARKs whose security and succeedness comes from using Merkle trees and codes. So some examples, the STAR protocol and similar protocols like Plonky, ReZero, Fusion. Venus is a new hash-based SNARK from last year. And yeah, in this talk, for simplicity, I will just focus on the standard STAR protocol, which is sometimes called if-STAR. At least that's the name it has in its documentation. So again, I will not describe how if-STAR works. I will only tell you what you need to know about it. So if-STAR is a SNARK that allows to prove instances of the so-called error relation. And we'll come back to this relation later. And the first message of the prover in if-STAR is a commitment to the witness of the following form. So it's a Merkle tree commitment to the low-degree extension of W. And I'll explain what's the low-degree extension of W. It's basically an FFT of W. And it's, oops. Okay, here luckily I repeated this part. Okay, so a big chunk, it's important to remember also that a big chunk of the whole if-STAR prover is spent on computing this commitment. It's easily half the cost of the proof. So these considerations raise some concerns about folding in the context of STARs. First, errors are not R1CSs, and we saw that Nova folds R1CSs. So that's the first concern. Second one is that here we are using Merkle trees to commit to the low-degree extension of W, but Merkle trees are not homomorphic, so that's another issue. And a third issue is that even if Merkle trees were homomorphic, would it be worth it to fold if each step of the folding requires us to compute this, which is most of the cost of computing a STAR proof? Would it be worth to go to go through the trouble of folding in that case? So let's discuss these issues. So when it comes to error and R1CSs, this is very simple. So a couple of years ago, or maybe a year ago, Sethi and Taylor showed that a degree D error is also a so-called degree D customizable constraint system. No need to know what's a CCS. So when the degree is 2, a degree 2 CCS is basically a relaxed R1CS. And in many cases, errors usually have degree 2 or 3. So let's assume they have degree 2. So we can think of errors as this degree 2 CCS, which is some kind of relaxed R1CS. So for the purposes of this talk, we will think of errors as relaxed R1CSs. They are not exactly, but they look like relaxed R1CSs, only with a little bit more complication. So since errors are R1CS, relaxed R1CSs, in principle you could use this Nova type folding scheme on the error relation. Okay. third issue, and I'll address the second issue later. The third issue was on the concerns of the cost of computing this Merkle commitment to the low-degree extension of the witness. So first of all, what's this low-degree extension? So the low-degree extension of a vector W with respect to a subgroup is obtained as follows. So the subgroup has the same size as the vector, and to obtain the low-degree extension, you do the following. You compute a polynomial that interpolates W, the vector, over H via an FFT, and then you compute the evaluations of F on a subgroup which is larger than H. And this is your low-degree extension. It's the evaluation of the polynomial that interpolates the vector on a large subgroup. And the ratio between the original subgroup and the second subgroup is called the rate, which is usually set to 1 from 1/2 to 1/16. And the rate controls creates a trade-off in stars between prover speed and proof size. So the cost of computing the Merkle commitment to the low-degree extension scales superlinearly on the inverse of the rate. So if we were to take the rate to be 1, which we cannot because of security issues, if we want to use SNARKs for the proof, then the cost of committing to the low-degree extension would decrease by 2 to 16. And yeah, and the size of the star proof scales linearly on rows. As I said, there's this trade-off. So yeah. So one thing we can do is observe. One of our observations is that we don't need to compute the low-degree extension when we want to do folding. Low-degree extension is only needed to achieve soundness through codings, through codes. If you're not gonna get cryptographic security from codes, you don't need to do a low-degree extension. And if we are only concerned about folding, then this means we don't need to do the low-degree extension. We can just commit to the W. And if we just commit to the W, imagine Merkle trees are homomorphic. Just by committing to W, we speed up the cost of this computation by at least 2, but it could be an order of magnitude. Okay, so here is our framework for folding hash-based NARs or code-based NARs. So recall that we want to fold error instances, and that we think of error instances as sort of relaxed R1CSs. And we are going to use a homomorphic commitment. So we are going to do NOVA with a homomorphic commitment. And at each folding step, we will compute the commit. We will use this commitment to commit to W instead of using the Merkle tree commitment to the low-degree extension of W. So importantly, we will not commit low-degree extensions or do any FFT when we do folding. Okay, this sounds nice, but there's a problem. When folding is done, we have to prove that the folded instance is in the accumulated relation, which means that we have to prove an instance of the original relation, and we have this claim about a commitment. However, as I mentioned, InfStar uses a commitment to W to the witness of this form, so Merkle tree commitment to low-degree extension. And our goal is to be able to use SNARKs. So this condition that with a SNARK we have to prove this. We have to prove that the instance witness is in the relation and that the commitment to the witness is some public value. And we have to use a SNARK to prove this statement here, because now we cannot just merge these two commitments together as I mentioned you do when you use NOVA folding. Now we have to prove that this commitment commits to the same vector as this one. Okay, so how do we do it? So we propose two approaches. Let's discuss one. So this is just a copy of the previous setting. So we propose two approaches. There's the direct approach, and in here we propose to use a SNARK, just use a SNARK to prove that the final instance witness pair is in the relation, and that the commitment, the witness you are using commits with this homomorphic commitment to W, to this public value. So here we have to be careful with what commitment com we use, because com could be very hard to arithmetize with an error. So we could take a Pedersen commitment and then try to prove this Pedersen commitment with stars, but it would be a nightmare. So we cannot just use a Pedersen commitment, because Pedersen commitments are extremely difficult to, extremely expensive to arithmetize as an error. Okay. And I think I'll skip approach 2 for now, and if I have time I will come back to it. So let's instantiate approach 1. We instantiate approach 1 by using the homomorphic, by taking the homomorphic commitment to be a lattice-based commitment scheme. And inspired by lattice-fold from Bonnet and Chen from this year, we take this scheme to be the itai scheme. And what's the itai scheme? So this scheme allows to commit vectors with entries in a so-called cyclotomic ring. So a cyclotomic ring is basically a Galois field. So it's an extension. So you take a ring of polynomials with coefficients in a field, and then you mod out a polynomial. So FP is a prime field, a field of prime order, and this is almost a Galois field, except that the polynomial you are modding out by might not be reducible, and if it's not irreducible, in general it is not, you get that R is basically, instead of a Galois field, it's a direct product of Galois fields. So a Galois field is a field whose order is a power of a prime. So these cyclotomic rings, if you're not familiar with them, you can think of them as direct products of Galois fields with some strange multiplication. And a very important fact about them is that the itai scheme can be instantiated for P star T prime, and by star T prime I mean baby bear, Mersenne 31, Goldilocks, or the 250 something bit field that Starnet is using right now. So this is very important because it will allow us to arithmetize the itai commitment scheme in a nice way over star T prime. Okay, so how does the itai scheme look like? So take a vector with entries in the cyclotomic ring. The commitment to this vector is simply the result of multiplying the vector with a matrix, and this matrix is a fixed matrix with entries in the ring. It's when you set up the commitment scheme, you sample this matrix randomly. The scheme is binding as long as the norm of the vector is small enough, and this is due to the MC's assumption, which says that if you have a random matrix, then it's unfeasible to find a vector with small norm, and such that when you multiply it by A, it's 0, and the vector cannot be 0. Okay, so this scheme looks very homomorphic. Why? Because the commitment to a vector is simply matrix multiplication, which is a linear operation. It is not, unfortunately, and I'll explain why later, but let's assume for a moment that it is. So if it is, then I already explained how we can instantiate our folding scheme. We just take this commitment as our commitment, as our homomorphic commitment, and do Nova folding. And yeah, so as I mentioned, when we want to prove a folded instance, we will have to prove a statement about an itai commitment. So we will have to prove that our witness multiplied by this matrix is some public vector, which is, so this is work in progress, but we expect will be reasonable to do, because as we saw, R is a direct product of Galois fields, where the base prime is a star prime, it's a star compatible prime, so we expect that operations over this ring will be relatively cheap to arithmetize over these fields as an error. Okay, so yeah, we benchmark the cost of computing the commitment to the witness versus the commitment to Merkle tree committing to the low-degree extension of W. And here, for clarity, the commitment is the ITI scheme. So this comparison is apt because if anything you would do with faulting, right now in the context of SNARKs you do it with recursion, and if you use recursion you do need to compute this Merkle tree commitment of the low-degree extension for each proof you are recurring over. So yeah, in this we run some benchmarks. These are the data we used. So we used a 32-bit field, and these are the results. So committing to W took between 100 and 400 milliseconds, depending on how we configure the parameters of the ITI commitment. And computing the low-degree extension plus the Merkle tree took this number of milliseconds for different rates. So as I said, the Merkle tree commitment scales super linearly on the inverse of the rate, and here we can see that indeed it does. In any case, the improvements are easily 10x. And yeah, so this is just one benchmark. Disclaimer: it's work in progress. We are also, so this benchmark is done. We are implementing and benchmarking the whole folding scheme. And yeah, and we also have to implement a SNARK proof, a method for proving the correct ITI commitment. Okay. I started a bit late.
Yeah, I know. Just I'm giving you a heads up.
Okay. Yeah, so the ITI scheme is not homomorphic. This is an issue. It looks really homomorphic, as I mentioned, but it is not. And the issue comes from the norm. So ITI commitments can only commit to small vectors. So if you add up the commitment to two vectors, you get a commitment to the addition of two vectors, which increases the norm. So you might lose bindingness here. So this is the crucial thing that the lattice fault paper addresses. So the lattice fault paper uses this ITI scheme plus some clever tricks to prevent the norm from growing. However, the lattice fault works over hypernova. We wanted to work over nova to not lose the structure of airs. And yeah, so to work over nova, we had to address a major issue, which was that nova has to commit to this cross term, which is quadratic on the witness. And this is something that in lattice fault they didn't have to do. And that was that's a big blocker for doing the lattice fault tricks. They just don't work. So what we did is we designed a variation of nova where P doesn't need to commit to T at all. So actually T, or the error term in nova, is implicitly committed by a commitment to the witness. So we replaced the commitment to T by an evaluation of T at a random point. That's the rough idea of our approach for this folding scheme. And incidentally, this modification to nova leads to easily 5x speed up versus the standard nova approach. Okay, and that's my talk. Thanks.
You just mentioned that we adapted lattice fault to nova and not hypernova. I didn't understand why, because hypernova supports CCS, and CCS you can somehow have air. I didn't understand why.
Because hypernova performs the first step of Spartan, right, during the folding scheme, and then it reaches some kind of linear constraint. And then it folds this linear constraint into a running linear constraint. And then so this requires running this first step of Spartan at each step of the folding process, which we didn't want to do. And when you are done folding, you have a linear relation, which is not really an error. It's kind of a very simple relation. So we wanted to do the folding at the beginning instead of in the middle of the proof.